Okay, AP Calculus BC, Unit 3, Day 3. We're going to do a review of optimization, which is an AV topic that we talked about last year. But we'll do a quick review of this. We are going to be, I'll just work through one example and kind of highlight the major steps that you need to take. So let's see. Okay. So you need a fence. You need to fence a rectangular area against a cliff, so there might be some natural boundaries on some of these problems. You have 100 feet of fence available. Probably going to use it all if we want to maximize the area. So trying to maximize the area. And we have 100 feet of fence. That's going to be the perimeter. We should draw a picture. So you have this cliff, and you're building a rectangular, you're going to fence in a rectangular. Now, these have to be equal because it's a rectangle, so that's going to be x and x, and this is going to be y, but we're not going to build anything here. You can use whatever letters you want. I'm just choosing x and y. So the first thing after you have a good picture is to try and define a function for the thing that you're trying to maximize or minimize. For us, that's area. And the area of a rectangle is x times y, base times height. Now, then we want it in terms of one variable. So instead of x and y, it could be all x or it could be all y. It can be either way. And there's some other constraint that they've given you. In this case, it's the perimeter, or at least the perimeter of the fence you're building. This is going to be x plus y equals 100. And now this gives you another way of relating x to y or y in terms of x. You can get whichever one you want by itself. If you solve for x in the way I've written the problem, you'll be able to get some fractions. So it's really just up to you how you want to do that. And so then we're going to replace one of them in terms of the other. So our new equation is x times parentheses 100 minus 2x, which I actually like to use this one. But I do want to distribute it also because that's helpful for a different. So I'm going to use both of these. So we have our function for the thing we're trying to maximize in terms of one variable. So now we need to find the candidates, the places where it could happen. And this is just extreme value theorem. And the endpoints are usually some other kind of form of constraint, just realistic or whatever. But the critical points, we're going to set the derivative equals 0 undefined. So we got to take the derivative of a, and so that's going to be 100 minus 4x equals 0 or undefined. And in this case, we get x equals 25. So that's your critical point. Our endpoints here are going to be, if we've chose to rewrite in terms of x, then endpoints can be x. If we chose y, then endpoints should be y. And what we're trying to do is say, what's the smallest x could be? Now, realistically, x could be 0. Cannot be negative. You cannot have negative fences, so just watch out for that. Sometimes x will have to be some positive number to ensure you don't get negative fences. The largest x could be, for me, so this is all y, right? Min x happens at max y, and if you want the other extreme of what's the biggest x could be, well, that would be all x, and that's going to happen when you have the smallest y value. So that's what I usually do. I say, well, what's the smallest y value? 0. And then you could use this relationship right here to figure out what the x is that goes with it. So that's going to be x equals 50. Okay, so these are our endpoints. And so now we're going to use extreme value theorem, hopefully, but if we can't, we can sometimes use some other ways of doing it. So extreme value theorem would be best, and so we could set up a table just to show our work. X, if you got everything in terms of x, you can put x here. If you did y, then you put y here. We're plugging these back in. Now, I like to use that factored version of the equation because it usually makes the math easier, but it does need to be the original thing, not the derivative. Okay. Sometimes people accidentally decide to start plugging these into that last thing that you had. So we have our endpoints, and our critical points, and we're going to just test them all. So if you plug 0 in here, you get 0 times 100 is 0. If you plug 25 in, you get 25 times 50 is 125 with a 0 on it. If you plug 50 in, you get 50 times 0 is 0. So here's your min. There's a tie, and here's your max. So now we're going to, write our answer. The maximum, let's see, maximum area is 1250 square feet. Now I probably shouldn't say X and Y unless they gave me a picture with X and Y on it, but so I'm going to try and describe it in terms of, because someone else could have put X and Y also, but in different places. So that could be confusing. So I'm going to say when the side, and we're trying to find all the dimensions, when the sides perpendicular to the cliff are, that's the X value, so that's 25 feet, and the side parallel to the cliff is 50 feet. So that's a good thorough answer. And I'm also going to ask you to justify it. So we're going to say by extreme value theorem, and then naming is not enough, by checking endpoints and critical points. Checking endpoints and critical points. So this is a good answer. Now, if for some reason we couldn't do extreme value theorem, we could try first derivative test. Now, first derivative test is really only for relative maxes and mins, but in some cases it might shed light on absolute maxes and mins. So if we put this on here, we would still find the critical point, and then we would test a value. I don't know, x equals, say, 0. In the derivative, it's positive, it's negative, it's increasing, it's decreasing. This critical point is a relative max. But because this graph goes down forever and down forever, this will be the absolute max. Now, if we were looking for the absolute min, then we would really have to bring in the endpoints and stuff like that and plug them in. And essentially, at that point, you're doing all this work anyways. Now, to justify this, it is annoying, okay? So this only works if there is only one critical point, or one critical point where you're looking. Helpful if don't have endpoints. And in that case, you can't use EVT. Then you might try this. But in general, let's do EVT as much as possible. Okay. Here's another quick example of an optimization problem that's a little less geometric. It says two non-negative numbers have a sum of 1. Maximize and minimize the sum of their squares. So maximize and minimize. It's going to be the same work to maximize and minimize, the same thing. The sum of their squares is what we're trying to maximize, minimize. So I'm going to call that S, and the sum of their squares, I'm going to call one of them x squared and one of them y squared. Now, I want to get this in terms of a single variable. So there's this other thing they gave us, that the sum of the two numbers, x plus y, equals 1. So now we can solve for y in terms of x, or x in terms of y. Y equals 1 minus x. I'm going to plug that in here. So s equals x squared plus 1 minus x squared. If we work this out, x squared plus 1 minus 2x plus x squared. S equals 2x squared minus 2x plus 1. So I'm just trying to clean it up. So this is our new formula in terms of one variable. We want to find critical points. So S prime equals 4x minus 2 equals 0 or undefined. So then x equals 1/2 is your critical point. Our endpoints, let's see. So it says they're non-negative. That means it could be 0 or positive. 0 or positive. And so I think the smallest one of them would be 0. So I think our endpoints for x, the smallest would be 0. And then the other extreme is that y equals 0. And so x would have to be 1. So these are our endpoints. And then we would set up a table. And I mean, we could use whichever one you want. You plug 0, 1/2 in, and 1. If you plug 0 in, you get 0 squared plus 1 squared equals 1. If you plug 1/2 in, you get 1/2 squared plus 1/2 squared is 1/4 plus 1/4 is 2/4 is 1/2. And if you plug 1 in, you get 1 squared plus 0 squared is 1. So this is the max, and this is the min. And so we're going to say the maximum sum is 1 when the numbers are 0 and 1. And this one's the same thing, 0 and 1, 1 and 0. It doesn't matter that one of them has x and y. We made those variables up. The minimum sum is 1/2 when the numbers are 1/2 and 1/2. And then I want you to justify it by extreme value theorem. By checking endpoints and critical points. So there we go. Now for your assignment, we will do this assignment, but I think we're going to go ahead and probably skip this assignment. So there you go. Go for it, try it, show your work, write your answers nicely. Even if the back of the book doesn't have these nice thorough answers, I want these nice thorough answers with justification. Okay.